The year is 1956. You've been having trouble deciding between right and wrong, but thankfully, a new computer program called the Logic Theorist is here to help with all your indecision. Okay, well, it doesn't exactly help with moral dilemmas, but it does produce answers for the most fundamental of logical problems. These problems are called theorems, and in the 1910s, a couple of guys named Whitehead and Russell wanted to prove everything that could be proved about logic. They made good progress, but were ultimately stopped short. Some years later, a few other dudes wondered if these theorems could be proved automatically by computers, and they went on to create what is considered by many to be the first artificial intelligence program. The logic theory machine works by having a set of axioms or ground rules for logic and used methods like substitution and matching to try out combinations of logical expressions until a theorem was proven. This program managed to recreate 38 theorem proofs from Whitehead and Russell's work. If a group of guys could make an automated proving tool in the 50s with what was essentially punch cards and chewing gum, how hard could it be for me, someone with a modern RGB-powered computer, to recreate? Before getting into the programming and development, let me briefly give some detail on what we're actually working with. There are really only three logical components that you need to know about: variables, or connectives, and implies connectives. A variable is pretty much what you'd expect. The letters we'll be using for them are P, Q, and R. Variables can be more easily understood through connectives like or and implies, which describe their relationships. For example, take the statement P implies Q, which is like an if-then statement. You'll notice implies is an arrow that has a direction to it. That means that just because P implies Q is true, it doesn't mean that Q implies P is true. For example, maybe P is being a human and Q is having a heart. If you are human, then you have a heart. But if you have a heart, that does not necessarily mean you're a human. The or connective means that at least one of the variables is true. Let's say P is it's raining, and Q is I have an umbrella. If it's raining but I don't have an umbrella, the whole statement is still true. Or if I have an umbrella but it's not raining, then the statement is true because at least one of the variables is true. Lastly, it could be raining and I have an umbrella, and the statement is true. Pretty much, we will be looking at logic theorems, which are statements like these, and trying to create automatic proofs that show these theorems are valid. For this project, I wanted to create a more visually compelling representation of what's happening during automated proofs, and thus I introduce the logolith. It doesn't look like much now, but watch this. Oh, it probably shouldn't have gravity. And now it looks like someone who can't find what they want in the grocery store. Alright, this looks better. And I gave it a radius to wander around in, and it's leaving. Okay. I had a vague idea of the logical pieces I would need, so I made a series of logical scripts and then created some corresponding objects. Before getting too far with the logic, I wanted to develop the body a bit more. My idea is to have a segment for each part of the logical expression. I tried using joints to get a nice bendy movement between the parts, but I clearly didn't set it up correctly. Surely gravity will help this time. Instead, I just decided to go with a custom follow script for each segment where it gradually turns. Okay, cool. That's looking pretty good. I added a couple minor tweaks, and I'm not sure what happened. I guess you could say it's a bug. Sorry. Let's revert that back. It's pretty satisfying to see this guy move around. You might have noticed this little cave thing off to the side. This is where the logoliths are going to come from. The number of segments they have should correspond to the length of the expression, and I have a basic building block that I'll spawn in for each segment. Let's try it out. Well, at least the head is there. And it's getting freaky again. With a few adjustments, all seems to be well. And we can spawn multiple of them. Let's add a spawn point. That looks good. And we can still make multiple. Okay, a couple more. Just a few. Kinda looks like a bowl of rice. Anyway, I wanted the connective segments, like or and implies, to be a different shape, so I got that set up. Cool. The different element types should also be visually distinct, so let's add some color. That's kinda hideous, but I can polish it later. And let's allow for different variable letters like P and Q to have different colors as well. I didn't mention this earlier, but some variables can have a not component, like not P or not Q, so I added a spot to visualize that. Alright, now that there's a pretty robust system in place to represent logic, let's tie it into the logoliths themselves. But how? I mean, I have these strings of symbols, and I can give each piece a value, but how can I actually handle substitutions and find logical equivalences? It was about this time that I realized I had no idea what I was doing. With not the faintest clue of how to compare expressions, I decided to build a new system from the ground up. And I did. 4 times. Okay, before getting into progress, I'll explain the plan for how to structure the order of the logolith. Here's basically how it works. Any expression will have a main element, which is implies in this case, and every connective element, like implies and or, will have left and right branches. Each logolith will have a game object for each of these elements, and the segments will be built off of a collapsed tree diagram like so. The creators of the logic theory machine use complex substitution and matching patterns, but instead of deciphering this alien language written in nerd hieroglyphics, I decided to use logic tables. Here's an example of 2 logic tables for expressions we'll need later on. The columns represent the value of the expression or variable above. So when P is true, not P, because it's the opposite of P, is false. And the statement not P or not P is false, because both elements are false. And we know or statements need at least one element to be true. Conversely, when P is false, not P is true. So not P or not P is true, because both elements are true. You can see that even though we have 2 different statements here, there's logical equivalence between the 2. We will leverage this logical equivalence later to determine when we can perform substitutions for the logoliths. Before doing these substitutions, the logoliths first need to be able to search for one another. This works pretty well, but I don't think we'll be seeing those 2 again. The idea is to have 2 camps, one for searchers and another for expressions that searchers can compare against, and for now they still don't combine. Here's how it looks with searching. They mostly just pile up on each other at the moment. I have it set up so with a button press I can make them search for another expression. Okay, I've already done most of the work for setting up the logic table comparison, so when these 2 creatures touch, we should get a replacement. At the moment, the 2 expressions are not P or not P implies not P, and P implies not P. We're hoping to get a replacement between not P or not P and P implies not P, because as we just showed, there should be logical equivalence. Well, it started to work. Let's not worry about deleting the other logolith for now. That's exactly what we want. You can see that this segment represented not P or not P. Now the new logolith has P implies not P. Now we can try another expression replacement with deletion, and perfect. We should have all the parts we need to prove the first theorem. Before that, I know you can't tell because I have everything time-lapsed, but the logoliths have been moving kind of slow for me. I've decided to speed them up the only way I know how. Okay, that's a bit too fast. I'll just stick to the time-lapse. To get this first theorem proven, I'll create 3 camps, and each one will have one part of the replacement. Let's try with just 2 one more time, and that still looks good. So now for the moment of truth. Wow, it worked. We actually got a theorem start to finish. Each element of the theorem has a game object, and you can see the collapsed list I talked about earlier over here. The theorems should have somewhere to go once they're created, so let's make that happen. Alright, we made a new spot for it, and it goes to the right place. I think I'll just have it get deleted on arrival. Great, that should be just about all we need to start expanding. Let's do a test with all the axioms in place to see if we can still get our one theorem. Good, yeah, it still manages to find its way. I thought I'd try throwing in some random small expressions to see if I could get any unexpected combinations, but not much resulted from it. At least it's nice to look at. Also, I've constantly been getting small errors here and there with nearly every test, so let's return to a more structured approach. First, I'll optimize the searching a bit. The logoliths still have trouble finding a new match if the one they first attempt is not compatible. They're kind of clingy. Let's correct their behavior. Now it looks like they get the message. I've been able to create the first theorem quite consistently. But for the second theorem, because one of the steps does not have a logical equivalence between the two expressions, I need to add a new method of comparison. I took inspiration from the logic theory machine and created a structural similarity check where if 2 expressions had the same number of variables and connectives in each branch, then a substitution could take place. After implementing the structural equivalence and adding a few more sub-expressions to the pool, this happened. From here I created a system that would generate random logolith permutations, but it ended up being too buggy to use. I wanted to get at least one more theorem proven, so I added a few more expressions to the list and hoped for the best. Okay, we managed to create a kind of visual proof for 3 different theorems. I could probably cherry pick some more expressions to prove more theorems, but I'm not sure that it would reveal much more. I also have the problem that the later expressions have these double negations, and my system isn't set up to deal with those. There are a lot of ways that this program could be improved, but I've dumped quite a lot of time into it, and I'm ready to move forward. Here's one last look at a finalized version. I would normally publicly post the project for anyone to try out, but the final version just ended up with too many problems. I even messed up something to the point where the first theorem proof is no longer working. This is probably the hardest project I had planned for the immediate future, so I'm confident I can make something more accessible for future projects. Thank you all for checking out the video. Until next time.